Hello everyone, please let's start. So please start attendance. Please may click on yes for present. Okay. So guys, what we have seen before, it was about spanning set. We have seen the meaning of spanning set. Yes. So please, now it has been 1 minute starting class. Please click on yes for present. Okay, Nora. Okay, no problem. Okay. So what we have seen before, it was 3.4 and 3.5 the previous week. 3.4, it was about a spanning set, and 3.5 about linear independence or linear dependence, right? This is what we have done before. So please, for those who join late, just write it here. If you didn't click on yes, no problem. Okay. Okay. So before we have seen the idea of spanning set and linear independence. And what we have seen about span means if we have a set of vectors which is spanning a vector space, means any vector in this vector space, we can write it as a linear combination of the vectors of this set. So we have a set of vectors, v1, v2, vk. We say it's spanning if any vector inside the vector space is a linear combination of this set. Linear independence we have seen also. If we have a linear combination equals 0, means the coefficients are all zeros, correct? Now, we will see what's the meaning of basis. In fact, basis, it's too simply, it's we say that a set is a basis, so it's a set of vectors. What is the definition of basis? Set of vectors is called a basis if it's span and linearly independent. So 3.4 plus 3.5 gives 3.6. If it's spanning plus linearly independent means basis. Okay, guys? Just a second here. Yes, I have to talk about assignment. Guys, don't forget tomorrow. Tomorrow we will have assignment 4, which is individual, not group. Okay, guys, and you have to submit maximum by Tuesday. No, it's not limited. Even if you see a timer, you have until Tuesday midnight. Okay, it's not limited. Even if you see a timer, the deadline is Tuesday midnight. Forget about the timer. Okay, guys, and it will be saved. Yes, if you click, for example, on true false, you click. When you come next day, you click and you click next page as usually. If you don't click next page, means it's not saved. But once you click next page, yeah, for sure it's saved, as we did in ICA. Similar. Clear? Okay. So you have it tomorrow at 8 p.m. And yes, Mariam. And you have to submit maximum next Tuesday at midnight. Don't forget to submit, okay, guys? So what you can do is to do your work. Don't submit until you are sure everything is fine, okay, guys? Submit only if everything is fine. It's better. Like this, you can modify as many as you want, as many times as you want. Clear? So, so basically here, if V1, V2, Vk form a basis for a vector space V, then they must be distinct. What does mean distinct? Means different from each other. Because if one of them is equal to another one, if one is equal to another one means, in this case, we have a set which is linearly dependent. And if we have also zero, assume one of the vectors is equal to zero. So here, instead of V1, we have zero. Then this set, whenever you have zero, this set is linearly dependent. So it's not basis. So basically, to have a basis, all of them must be distinct, means different from each other. Then none of them is zero. All of them is different from zero. Okay? Because if you put the vector, the zero vector, then you will get a linearly dependent set. Is it clear, guys? Please don't miss it. It's always like this. If you have zero vector, means you have linearly dependent. Or if you have two vectors, also it's linearly dependent. Two similar vectors, also it's linearly dependent. Okay, Khalifa. Okay, Noura. So let's see an example here. What do we have? Example one from the textbook, page 199. So we have here a set of three vectors, E1, E2, E3. We want to see if this set is a basis for the vector space R3. So here the vector space is R3. We want to see if E1, E2, E3 form a basis. Okay, guys? So let's see if it's span. Span R3. So we write the definition. A1, E1 plus A2, E2 plus A3, E3 equal V. Any vector here. Now, directly we move to augmented matrix. E1 is 1, 0, 0. E2 is 0, 1, 0. E3 is 0, 0, 1. And V is ABC. Correct? So here we write the definition, and here we have the augmented matrix. Now, is it consistent? So we have A1, A2, A3. I have reading 1 for A1. I have reading 1 for A2. I have reading 1 for A3. So it's consistent for sure. The system is consistent. Okay, Maria. And so E1, here we call it E1. E1, E2, E3 spans, because I'm taking a set, spans R3. So here I call it E. I call it E1, E2, E3. Now, for linearly independent, let's see the linear independence. Can we use determinant here? We have number of vectors equal 3, n equal 3, so k equal n. Yes, we can use determinant. So let's see the determinant of E1, E2, E3. It's equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Yalla guys, what's the determinant of this matrix? Very good. It's 1 because identity, and it's diagonal matrix. So we multiply the entries of the main diagonal. Different than 0, so E1, E2, E3 is linearly dependent or independent? Independent. So we have a set spanning the vector space, and it's linearly independent. What's the conclusion? Here, n, r to the power of n, as we did before. So conclusion, E1, E2, E3 is basis for what? For R3. Correct? Very good. What do you mean does not belong? No, it belongs for sure. It's basis. It belongs also. Every vector belongs to R3. We have all vectors in R3. No, pay attention. Okay? Okay. Yes, come on. So now we have a basis. Now tell me, what's the dimension? What does mean dimension? to simply dimension here means the number of vectors in the basis. So you count. For example, if we have vectors, you count how many vectors. If we have polynomials, how many polynomials. If we have matrices, how many matrices. So here, dimension of R3. Here we have R3. So where is the basis? Here, this is the basis. How many vectors inside this basis? How many do we have? 3, too simply. So the dimension of R3 is 3. For that, you say when you have R3, you say we are in 3D. 3D means 3 dimensions. Okay, guys? Because we have a basis which has, because any basis of R3 has 3 vectors. So the dimension is always fixed, but the basis, we can find many bases. For example, if we multiply E1 by 3, also it's basis, new basis. But basically, you must get always 3 vectors. If you have 4 vectors, it's not basis for sure for R3. If you have 2 vectors, it's not basis for R3 because dimension of R3 is always 3. Is it clear, guys? Dimension is always something fixed. Is it clear? Okay, very good. So please take screenshot and let's talk about natural basis and standard basis or standard basis. Okay, let's erase. Here we can keep it, no problem. So guys, here we have natural basis. E1, E2, E3, we call it natural basis or standard basis of R3. No problem. So in general, the natural, this is very important, natural basis of Rn is E1, which is, look, what does mean E1? Means you take the first component equal 1, others all 0, and the rest, the remaining all zeros. E2 means you take the second component 1 and others 0. E3 means you take the third one 0, 1, so here third, and others 0. En, you take the last one equal 1, others 0. Understood, guys? For example, and this one is basis. So later we will see what's the dimension of Rn. What do you think? From look E1, E2 to En, from 1 to n, how many numbers? We have n, so it's the same here. Let's check, for example, natural basis or standard, okay? We say standard also. Of R2 is, how many vectors here? We need only 2. E1, so we take the first one, Z1 equal the second 0, because we don't have any more. And E2, very good, 0, 1. So what's the dimension of R2? 2, simply, we have 2 vectors. Natural basis for R3, look, 1, 0, 0, 0, 1, 0, 0, 0, 1, we see it, we have it. Let's see last one, natural basis for R4. Not of, we say 4. So here, how many components? What's the first vector? So we have 4 components. So the first one, other 0. 1, 2, 1, 2, 3, 4. Second one, so 0, 1, 0, 0. Very good. Third, 0, 0, 1, 0. And this is the last one. So count how many we have. Dimension are 4 equal 4. So basically, dimension of Rn is equal to n, always true. Is it clear, guys? Please take screenshot. It's very, very, very important. Is it clear, guys? This is very important. For that, I'm going very slowly. Please, it's very, very, very important. Very good. Okay. So now we can continue. Now let's see some polynomials. Always we take vectors and we take polynomials. So here, example 2 from the textbook, page 200, we have a set of 3 polynomials. So here we have p1 of t, here p2 of t, and here p3 of t. So we have 3 vectors. We want to show that these vectors or these polynomials form a basis for the vector space p2. So what should we do, guys? Check span and linear independence. Very good. Very good. Let's check spanning. And span. Always, guys, you need span and independence. For linear independence, can we use determinant, guys? Pay attention, we use determinant only for vectors. For polynomials, yes, very good. If you use it for polynomials, I will put, it's not allowed. So for span, let's see if it's spanning. So we write the definition always, and p1 of t plus a2 p2 of t plus a3 p3t equal p of t. Here we can write the augmented matrix. So what should we write for p1 t squared? And what should we put? 101. Very good. So t squared, 1t squared, 0t, and number alone 1. p2, 1. p3, 0. Very good. 0, 1 minus 1. and 0, 1, and 2. And P of t is ABC. Now we have leading 1. We make everything below it 0. Here already 0. Here R3 minus R1. 1, 0, 0, A. 0, 1, 1, B. 0, minus 1, minus 0, minus 1. 2, C minus A. We are lucky we have directly here 1, leading 1, so we cancel minus 1. R3 plus R2. So we get 1, 0, 0, A. 0, 1, 1, B. 0, we add them. 0, 3, C minus A plus B. That's 1, 0. Yes, Abdullah, here P1 of t. You take t squared as we did before. T and number. How many t squared do we have for P1? Look, 1 t squared. So you put 1 t squared plus 0 plus 1. Plus 0 t plus 1. Okay? Clear? Okay. 1, 0, 0, A. 0, 1, 1, B. 0, 0, 1, C minus A plus B over 3. Now, is it consistent? What does mean consistent? Means we have row 0 equal number. Here I have leading 1, I have leading, I don't have 0, so the system, no, it's by per column. The system is consistent. So, very good. P1 of t, 2 of t, look, because here we have P2, so we have to use P2 of t. We have to say P2 of t. And P1 of t. P1 of t, P2 of t, P3 of t. As set spans P2. So it's fine for now. Let's check if it's linearly independent. So we say we cannot use determinant because we have polynomials. So we have to use the normal method as usual. Write the definition. Linearly independence. So we will do the same, but instead of ABC, we put what? Put zeros, right? So we will take the same, exactly the same. What do you mean t squared plus 1, Abdullah? Okay. So for linear independent, so we will do the same. A1, P1 of t plus A2, P2 of t plus A3, P3 of t equals 0. And we write the augmented matrix. So it will be the same, but instead of ABC, you put 0. So it will be 1, 0, 0, 0, 0, 1, 1, 0, 1, negative 1, 2, and 0. And we do the same operation. So R3 minus R1, 1, 0, 0, 0, because here you have 0 linearly independence. It seems you didn't revise linear independence. Correct? So look, I'm reproducing this one, but instead of ABC, I put always 0. I have 3 divided by 3, so we get 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 1, 0. So you see, it's the same. Now here we have leading 1, leading 1, leading 1, similar. So is it linearly independent, the set? We have unique triple solution. So P1 of t, 2 of t, P3 of t is linearly independent. So we have 1 span, 2 linearly independent. So conclusion, is it the basis? Very good. It's a basis. And what's the dimension of P2? So dimension, you can get it from any basis. Is a basis. And what the dimension of P2 is. Now, how many polynomials do we have? Pay attention, yeah, it's 3. Very too simply. 3. So you see, it's different than Rn. Dimension of Rn is n, but dimension of Pn, it will be, what do you think? It's n plus 1. Okay, guys? I see A2, it's not next week, week after. We are in week 12 now, right? So it's week 14. And week 15, we'll have quiz. So next week, you will submit an assignment for week after ICA and week after quiz. Clear? If there is any update, then I will tell you. But for the moment, it's like this. So please take screenshot for this one. It's very important. Do you have any question, guys, so far? So basis means span plus linearly independent. Dimension is the number of elements. How many vectors inside the basis, or how many polynomials inside it. Okay. So here we have the solution. Now we have here 3 vectors. We want to see if V1, V2, V3 is a basis for R3. If we have 4 vectors, what do you think? It will be a basis? No need to think about it. Directly we say the number is different than the dimension. Dimension is 3, so we need 3 vectors. And if we have 3 vectors, we have to check if it's span plus linearly independent. But if we have less than 3 or more than 3, directly it's not basis for sure. Clear? Because to have a basis, you need three. You had the same, you need a set with number of elements equal to dimension and to be span plus linearly independent. But if the number is different than dimension, then no need to prove it's span, no need to prove it's linearly independent. It's not a basis. So here we have three. Maybe it's basis. We have to check if it's spanning plus linearly independent. Okay. But if we had four, directly we stop. We say no, it's not basis. Or if we have two, it's not basis. Any number different than three, directly we can say no, it's not basis. No need to prove it. You understand what I mean? Okay. So let's see here if it's span and linearly independent. One, span. A1 V1 plus A2 V2 plus A3 V3 equal B. Now we write the augmented matrix. V1 is 1, 0, 1. V2, 0, 1, negative 1. V3, 0, 2, 2. And V is ABC. Correct? Yes, yes, Abdullah. If we had four vectors in R3, it's not basis for sure. Always R3. What's the dimension of R3? It's 3. You need 3 vectors, which are linearly independent and spanning. R3 minus R1. 1, 0, 0. A. 0, 1, 2. B. 0, negative 1, 2. C minus A. R3 plus R2. A. 0, 1, 2. B. 0, 0, 4. C minus A plus B. Now we divide R3 divided by 4. So 1, 0, 0, A, 0, 1, 2, B, 0, 0, 1, C minus A plus B over 4. Isn't it? Do we have 0 equal number? I have all with leading ones. I don't have any, it's not inconsistent, so it's consistent. The system is consistent. How many solutions here? It's unique. So V1, V2, V3 spans R3. So one is done. Now, let's see if it's linearly independent. Can we use determinant? Since we have vectors, very good. So we have how many vectors? 3. It's r to the power of n equals 3, so k equal n. Let's see determinant v1, v2, v3. It's equal determinant of 1, 0, 1, 0, 1 minus 1, 0, 2, 2. So let's take the first row since we have a lot of zeros. So for the first row, it's plus minus plus. It's like this, right? This is a determinant. So if we take the first row, 1, we don't change the sign of 1, so it will be 1 times height 1, row and column. So we get 1, 2, minus 1, 2. So we get 2 plus 2, 4, different than 0. So is it linearly dependent or independent? is linearly independent. So finally, is it basis? Conclusion in black. Very good. V1, V2, V3 is, you see, it's different than the standard basis. Remember the standard basis, it was 1, 0, 0, 0, 1, 0, and 0, 0. Here is different, but how many vectors do we have? 3, because dimension is 3. Basis 4 are 3. And you see, we have the same dimension. Dimension is always something fixed. Is it clear, guys? Very good. Please, all of you, can you confirm that everything is fine? Very good. Easier, easier than making REF, because here also we have number of vectors equal to dimension. Okay? Determinant sometimes is easier. Okay. Here, I think this one will stop here. After the slide, we'll stop here. This one. So, look here. This is the definition. We did it before. What does mean dimension? Non-vector space is the number of elements in a basis for. We write dimension of V for dimension. Also define for the vector space 0, the dimension is 0. We don't have any dimension. So even here definition, we know it. No need for definition. Now, guys, we have seen the standard basis for Rn, right? Now let's see the standard basis for Pn. The standard basis for Pn. Okay? So we have seen the standard basis for Rn. Now standard basis for Pn. So first of all, who knows what's Pn? It's the set of what? It's an t to the power of n plus an minus 1 t to the power of n minus 1 plus etc. plus a2 t squared plus a1 t plus a0, isn't it? Such that all here, all coefficients here, this one, this one, this one, this one, this one are numbers. an minus 1, etc. a2, a1, a0, all not any numbers. So, what's the standard basis now? As we did before, standard basis for Pn is, look guys, you start with Tn minus 1, and etc. T squared, T and 1. Okay? Can you count? Who knows how many inside this set? How many polynomials do we have? False. No, it's not n. Okay, let's see standard bases for Pn. For P1, guys, is for P1. So what's the maximum degree is 1. So you start with T and 1. Now P2, standard basis for P2. So you start with T squared, T1. Standard basis for P3. Yalla guys. Very good. T cube, T squared, T1. Standard basis for P5, let's say. So we start with T to the power of, very good, 5. Then T4, T cube, T squared, T and 1. Yalla guys, tell me, what's the dimension of each one? The dimension of P4, P5. Very good, 6. So here we get n plus 1, very good. Dimension of P1, it's 1 plus 1, 2. Dimension P2, it's 2 plus 1, 3. Count here, 1, 2, 3, correct? Dimension of P3, 4. Very good, guys. Very good, all of you. So you see, basically the dimension of Pn, it's n plus 1, not like Rn. Rn, dimension of Rn is equal to n. Dimension of Pn is n plus 1. And now we know the standard basis for Rn and the standard basis for Pn. Is it clear, guys, all of you? Okay, very good. Due to some students, they lost the previous Sunday, so we will stop here to be with them. And next, this Thursday, we finish chapter 3. So next week, we will start new chapter, chapter 5. So I think we'll stop here. Do you have any question, guys? Thank you very much, and see you on Thursday, inshallah. Thank you, guys.